And I think he developed lithium sodium ion battery. And what is specific by Ismael Saadoune, he's doing everything in Morocco. He work in Morocco. He make research in Morocco, and he take his know-how to conference around the world. He even got a prize in Japan, I remember, I guess. So I will not go through his biography because I know him very good, but he's really, believe me, a very good scientist and very good man, very good friend. And I want really to thank him very much for all what he's doing for the country. And I want to give him the floor to talk about this subject, recent progress in lithium and sodium phosphate based electrode for high efficiency lithium sodium ion battery. The floor is yours, and I think my colleague behind the scene will open for you the Zoom to talk. It's already there.
Thank you very, very much, my old and inspiring friend, Si Ahmed. Really, I am a little bit emotionated. I don't know if you can say that in English by your kind word. So thank you for this nice introduction. And thank you and Professor Hajjaj for the kind invitation to give this talk, to present this technology that everyone is using or knowing somehow. Yes, I accepted the invitation very spontaneously, but I have also another reason to accept this invitation to give this talk to Jadida, because I'm originated from Jadida. I'm Dukkani. I'm good. I'm Dukkani. Even my color is going to black guy. I am from Sidi Ismail. Sidi Ismail is not so far from El Jadida, and everything happened in Jadida concerns me. That's why I accepted very spontaneously the invitation. So yes, allow me to give you in this 30 or 25 minutes some insight about lithium-ion battery. I will focus on phosphate. I'll just give you some idea. And then I see that in the program, we have also the talk from Ilyas this afternoon, who will also complement what I will say during this 30 minutes. So yes, as Ahmed said, we have batteries everywhere. Everywhere we have batteries. I can't put I don't know if I can put my laser. No, sorry, not that one. That one. Pointeur, option pointeur visible. Okay, I don't know if you see my cursor, but anyway, lithium-ion batteries are everywhere, even for the small energy sources application like smartphone, laptops, in medical application, or in some power tools. We have also application of lithium-ion battery in moderate engine like vehicles or trucks or something like that, or some bikes or something like that. But we have also application of lithium-ion battery in very huge application to store solar energy that are intermittent, and you know that for that reason we need a very big amount of batteries. But storing electricity is not possible. We can store water, we can store food, but electricity we cannot store as electricity. We should transform this electricity to another form of energy to store it, but we should have this reversibility to get more rechargeability. So electricity should be changed, and for battery, this is a simple but somehow complicated transformation of electrical energy to chemical energy during charge, and during discharge we have chemical energy transformed to electrical energy. So for any application from few watt hour for this small application to megawatt hour for the big application, the principle is the same. The principle is the same. It's the same. The difference is the size, only the size. But why lithium-ion batteries are so interesting? Because they have the two big features. We have a high power for this battery comparing to lead acid battery that we have in our engine actually, and they have this specific energy. So to make it clear, so we need a system that have big autonomy. Like Awita, he's a good guy for long distance. So we need some source of energy to power our engine for long distances. But we need also a source of energy that can power very fastly our engine. That's why Hussein Bolt is the good example, because he's a good guy to have this sprint in short distance but with high power. So lithium-ion batteries, as you see, are combining the two features, and this is why they are attracting more application that I highlighted in this figure. So, as you know, also Morocco start to attract a lot of gigafactory working on lithium-ion battery, like in Europe, like in Asia, like in America. You see here is in Europe, a lot of gigafactory working on different kind of battery, but in different component of the battery, cathode, electrolyte, or anode. And you see we have KTL, BYD, Volkswagen, we have LG and so on in Europe. But in Morocco also, we start to attract a big gigafactory, of course, with the joint venture with Chinese, because they have excellent experience and expertise. And you see here, we have this gigafactory in the north of Morocco, in Tangier, working on graphite. We have this Goshen that signed with the Moroccan government, the implementation of gigafactory in Bourknadel, not so far from Rabat. And of course, as we have this in Jaflasfar, where OCP plant are existing, and we are attracting a lot of gigafactory working in some cobalt, because we have cobalt. But you see here, they are trying to implement activity around LFP or NMC. I will explain to you later what means LFP or LMC. Of course, this is just some example, but for sure, many other gigafactory will come to Morocco for many reasons. One of the big reasons is that Morocco is near the supply chain, because in Africa, we have a lot of mineral resource that can be introduced, that are used actually in commercialized lithium battery, but also because of Morocco is not so far from Europe, and this is like a big market, but a closed market, and the shipping will be very, very cheap to deliver batteries or to deliver vehicles for Europe, where the energetic transition is ongoing. So briefly, lithium-ion battery is not lithium battery. We started first by lithium battery. We're using lithium metal, okay? Lithium metal, and we have a cathode material on the cathode side. But unfortunately, during charge and discharge of battery using lithium metal, we have this phenomenon, what we called lithium growth. So lithium metal, which is a metallic, is conductor, start to develop what we call some dendrites. And during cycling, we have a short circuits between lithium metal and the cathode material that can cause some safety issues. That's why Sony in 1991 have this big challenge to replace lithium in the anode side by graphite. And we don't have lithium metal in the system, but we have only ions, lithium ions in the system that are moving from the cathode side to anode side during discharge. This is transformation of electrical energy to chemical energy. And during discharge, chemical energy is transformed by the transfer of lithium from the anode side to cathode side reversibly. That's why we call it lithium-ion battery instead of lithium batteries. And you see here the quantity of lithium moved from one side to one side is proportional to number of electrons going there. So the capacity of your battery is proportional to the number of exchanged lithium. And also the difference between the voltage between the graphite is the anode and the cathode material. Here is lithium cobalt oxide, because he was the first one commercialized by Sony, and the difference gives you the voltage. And the stored energy in watt-hour is the voltage multiplied by capacity. So the aim of any industrial is to have a high voltage between the cathode and anode to select the right cathode material and the right anode material, and also having a big exchange of lithium during cycling, charge, and discharge process. So a new development and new solution. Of course, we are approaching the asymptote. There are no big breakthrough of new material, but I think I will show that later. Artificial intelligence could help having many good material for the future. So in the anode side is well established. This graphite is the best one to use in the anode side. And if you make a calculation to calculate the capacity, and you see here we can have the capacity of like 370 milliampere per gram, but we have also a new good anode material is silicon. And with this silicon, we can get like 10 times what we have in graphite, but we have some problem with silicon. And the future is, this is like indication for the young people, is to use this mixture between silicon and carbon composite as anode. And you see here the market is growing year by year. And in 2029, we expect to get like $16,000 billion for market of just the anode side, just graphite. And the cathode side is very challenging because there are some criteria that are necessary, but sometimes doesn't work. So there are some criteria here, like that the cathode should have lithium in this initial formulation. It should contain also some transition metal ion because we have oxidation reduction during the process. And it should also have a good reversibility with lithium because we are doing this efficiency. We should charge and discharge without losing many energy. And we have also this big challenge. We have this periodic table you see here, and we have plenty of elements. And to develop a new cathode material, we should have this in mind. Should have abundant elements because of the cost, of course, and sustainable development, because this is one of the big criteria to commercialize, to marketize your products. And for that, I know that there are a lot of artificial intelligence approach to take in account this sustainability and cost of element, and taking in account the criteria of selecting the good cathode material, and also the big data, because we are working on the cathode since 1991. This is more than 35 years, and there are a lot of work, and I think artificial intelligence and machine learning could help to select the best one. For the engineering, this is very important because in Morocco we need to get this expertise of engineering, not only in lab scale, but also in the industrial scale. So how to proceed? The process is the same in the anode and the cathode side. What we do is we prepare a slurry composed from the active, is graphite in the anode. We add the solvent, so sometimes they are organics, carbon to enhance the conductivity, and the binder to have good mechanical cohesion of the particles. And after that, we coat this mixture in the copper foil here in the anode side, but in the cathode side, we have aluminum foil here by using the roll-to-roll process. And then we should have this calendering. Calendering, what means is we should have a good contact between this slurry, this powder, and this collector, current collector. That's why we put a press, we compress to control the density and also to control the contact. And after that, we have this drying process because we have solvent at the beginning. We should remove this solvent during the drying process, and then we can cut and punch electrode depending on the size of the battery. And the size of the battery are different. We can have this coin cell, that's small, some few micro watt hour, to cylindrical cell, to pouch cell, and to prismatic cell. It depends what we would like to have in the application, but the process, as I said, is exactly the same. And we should now, in some labs, we know how to proceed for the coin cell, but for pouch cell and so on, this is a big challenge. And we see that we have a big gigafactory coming to Morocco. We should have learned to our engineer, our student, how to proceed going from small size to bigger size, which is very, very strong story and difficult story. So some of actually commercialized material you see here, this is the cathode material that are now in the market. If you Google, you can see battery LFP, battery NMC, and so on. And LFP means that it's lithium iron phosphate. That's why OCP, as Ahmed said, is interested to develop this material because we have this resource in Morocco, and LFP is going to get a good market. You see here the development of the market of the different chemistry from LCO is lithium cobalt oxide, NCA is nickel cobalt aluminum, and so on. And you see he's in pink LFP from 2020, there are no big work, but you see here the expansion of the market. That's why we are going to work on that subject. So you see here, this very briefly, yes, the raw material, you see China have the biggest, but others is Africa. The raw material are existing in Africa and some country in Latinos. But during the process and during the component lithium cell, you see that Africa disappear is here. It's only China in the market. That's why to get this sovereignty on producing material, producing cathode, producing battery, we should have a good decision inside Morocco, but in Africa to produce, to be not only consumer, but also producer. It will be very hard, but nothing is impossible. Let me briefly give you the challenge of battery. I just have to look to the time. Okay, the challenge, the big challenge, the future challenge of batteries to introduce phosphate. Of course, they are more than 8, but here I summarize 8. We have the cost. Of course, we should have to lower the cost, to have higher density, energy density, and to have safety because of the user could not have some safety issue, and this long time of first life. And for this, all this reason, the polyanionic in general material are, including phosphate, are the good and the perfect candidate to meet with all this challenge. And phosphate, with this Nazi-Con type structure, for the atomic point of view, have this good crystalline future. They are stable structure, so we should have many cycle charge discharge for a long time, no problem. They have fast ion conductor for lithium or sodium, so we can have good power, fast charge, fast discharge, and so on. And they are more sustainable because phosphate are coming from the earth, so no problem to use it and to put it in the earth after using. That's why these are very important. So let's go for safety. Here are some pictures from some recent problem that overcome in France or in South Korea or in China, and there are sometimes spontaneous burning of battery, but sometimes there's some abuse of this battery. But when looking of this kind of chemistry inside this battery, we see that we have only NMC, and NMC is like oxide. And you see battery is a closed space, a closed engine, and to have this combustion, we need oxygen, and oxygen in general coming from the oxide, from the cathode material. That's why polyanionic like phosphate are much more safe, because the oxygen is more linked to phosphorus to have this PO4 unit here. PO4 unit is very stable, and oxygen cannot be released from the structure to impact or to induce this flammability or this safety issue. So there are many causes of this safety issue. There's some mechanical abuse like penetration or crush. There's some electrical abuse like short circuit or something like that. There's some thermal abuse. And as you see, this abuse can induce some smoke, some fire, some explosion. And you see the cathode oxygen release. This is what I am saying. And the cathode oxygen release is coming from the oxide, from NMC type electrode. And now this is justified why LFP phosphate are good now for safety for lithium-ion batteries. So to make it clearer, why we have this good safety for battery, for phosphate, because of the high covalency of PO band, high structure stability, and better safety. And you see here, this is LFP, for instance. During charge, we can remove all lithium. And this, if you have a huge quantity of lithium, this means high capacity. And during discharge, we can get back to the all lithium. So we get hold of existing the capacity in LFP. In the case of NMC, the structure is layered like this. And lithium here is like stabilizing the NMC structure. If you remove all lithium, the structure collapse and your battery will die. That's why we are using only like 60 or 70% of lithium of the existing capacity. This is one of the reasons to encourage people to work on LFP-based material. And for NMC, we have this problem of structure stability, but we have the problem of oxygen release that cause this safety issue. Of course, there are a lot of work on LFP. I'm not going to give you the details, but the process is very important. The process to produce good LFP. LFP, the cost of LFP can range from $10 kilos to $20. It depends on the quality of the final product. And the quality of the final product depend on the process. There are a lot of processes like hydrothermal, iron red, iron phosphate, and so on. And the synthesis depend. We are working on that. It's very, very challenging because when we are thinking about marketization and commercialization of the product, we should think about many things. And temperature, time, precursors, atmosphere, carbon source, pH of solution, and so on are very important. And here also we can introduce artificial intelligence to select really the good parameter to get the good LFP. But the problem of LFP, of course, they have a low conductivity, and of course they have low voltage. You see here, I compared the voltage of LFP is here in red and NMC in blue, and you see we have difference in voltage. And remember, the energy density is voltage multiplied capacity. This means that, of course,
Professor Saadoune, you have 5 minutes.
Okay, I'm over. So that's why we should have improved this voltage to higher voltage. So this is why there are two approaches. One is how to put manganese, and now there are a lot of patent, a lot of work to have manganese inside. And you see here, the first voltage was 3.5 volt, and now we are going to 4 volts. So we increase the voltage, then we increase the energy density. The second approach is how we introduce fluorine, because OCP is producing phosphate, but it's producing also fluorine. And we develop this new material, and you see here, I compare the voltage of LFP with the voltage of our material, and you see we improve from 3.7 to 4.3 volt. This means that, and we see here that we have good stability. Let's go to sodium very briefly, because I don't have time, because one of the challenges is the cost. And sodium battery could be the good solution. Why? Because of the cost. You see, we compare here the cost of source of sodium, and you see this is the big difference of the difference. And sodium is everywhere. In Morocco, we have an ocean, we can have sodium. And there are now many gigafactories work on sodium battery using iron oxide or some phosphate, polyanic compound, and so on. And for that, just give you how it's work. During charge, of course, we are working on this sodium phosphate. And you see here, we develop material. This is very important to optimize the process. And we got good result. We have this carbon existing in the structure. This means that we have good conductivity, most power. We are using techniques for solid-state chemistry to be sure that we have iron 2+ in the structure. And then when charge and discharge, you see that we have a good reversibility of the process, and we have this phenomenon. And to understand now, once again, we have to use our expertise in solid-state chemistry to understand why we have this discharge here when putting vanadium, and we explain by using impedance. I will finish by this one, which is very important. You know, this gigafactory is Tiamat, is using this cathode material using vanadium, phosphorus, and fluorine. And we develop our scalable and efficient process using as some alternative. This is our approach. And you see here, we develop a good material, vanadium-based, but you see during cycling, we have 160 million, which is comparable to LFP with low-cost material. And this is a good way to develop also in our laboratory. This is my conclusion. Digitalization is also one of the big challenge of future. And you see, we can use artificial intelligence. Remember, during the battery design, material discovery, I told that before, the manufacturing process, how to prepare cathode from raw material, so to get process control, yield improvement. The battery management, of course, we are producing cells, but from the cells, we will produce module and then pack, and BMS will play a big role to manage energy inside, and artificial intelligence could help. Charging optimization, because everyone would like to have fast charge, but we should reduce stress on the battery, and then this digitalization can help. And also recycling, because we have a lot of wasted batteries, and we should recycle, and using artificial intelligence could help on this matter. So I'm sorry to be late, but I would like, before finishing, to thank, of course, our university and OCP and Fondation OCP for funding our research and to believe in our research, and also the students and PhD students and postdocs that